Okay, today we will cover a topic called dimension and units. This is the two concepts are extremely important in physics and engineering problems, and we will go through what they are and also how to operate on them and how to use them to check the physical meanings of quantities. So let's look at their definition. What is a dimension? Dimension represents the nature of a physical quantity. So to represent the nature of a physical quantity. The nature means we describe how what's the length of the quantity or how long the duration. Well, that's the nature of it. And then when we talk about units, it's standardized description of the size or amount of that dimension. So it's standardized description to the size or amount of that dimension. Units describing the same dimension can be converted. For example, you can describe length by using meters or using centimeter. And you can convert units by saying, for example, 1 meter equals 100 centimeter. And then that give you a rule of conversion. But the dimensions themselves cannot be converted between each other. So you cannot convert a dimension of time to a dimension of length. That's obvious. That's why you only heard the people say unit conversion and the people never say dimension conversion. Now, let's think about physical quantities. There are two types of quantities. One is called a dimensional quantity. Dimensional quantity has a unit and a dimension. For example, if you describe a mass of an object, you say the mass is 1.5 kilogram. It has a unit, the unit is kilogram. It also has a dimension, the dimension is in the dimension of mass. And you also have a force applied to an object, 2.3 Newton, and the dimension is in force, and the unit is Newton. So those are dimensional quantities. When you see a physical symbol like M or F, they inherently carry dimensions, and therefore you do not need to write units when you use them symbolically. And if you want to take the dimension of a physical quantities, you usually use the notation square brackets, means take the dimension. For example, the dimension of mass is this M, a physical symbol represent mass, is capital M. So capital M is the symbol of a dimension of mass. And there are some common symbols for some common dimensions. And for example, length is L, and the time T. So those are standard symbols represent a dimension of a quantity. And one thing you always need to be keep in mind is whenever you write a physical quantities, you always need to specify its unit if it doesn't carry units. What I mean is, if you are drawing a free body diagram and you are saying what's the gravity pulling on this object, there are two ways you can do this. You can say it's just mg. These are totally valid because when it's represented in physical symbols like m and g, the symbol itself automatically carries dimension, so you don't need to specify what it is. However, if you prefer to use numbers, then if you are saying, okay, mass multiplied by gravitational constant, if the mass is 1.5, you must specify what's the unit. For example, in this case, let's assume it's a kilogram, and then multiply by the gravitational constant, which is 9.81 meter per second squared. And this is another valid way to write this. So for symbols that already carries units, you don't need to put units after symbol. Sometimes I saw students put like units on the after symbol. For example, they would say m kilogram. But those are totally like incorrect notation, and nothing like this is like legitimate. So you cannot do this. Now the second category of quantities are called non-dimensional quantities. Non-dimensional quantity, it just means it's a physical quantity, but it doesn't carry any dimension. For example, if you count how many number of apples on the table, you are saying, okay, there are 5 apples, then n equals 5. 5 is just a number, and then it's a number of items. Then you don't need any units or dimension after it. And some other physical quantities, they inherently don't carry units. For example, we have strain. In mechanics, if we have learned the stress and strain, strain is defined by du. Well, let's don't use d, let's use gradient so that we can more generic in 3D. So it's defined as the gradient of displacement. And then when you take the gradient, if you look at the strain along the x direction, then you have the displacement along the x direction. And then take derivative with respect to x. Then it will give you a dimensionless quantity. For example, you may have strain along the x direction, xx is, for example, it's usually very small, 2.1 times 10 to the minus 4. And that's it. It's a number. It doesn't have any dimension. So you can also put several dimensional quantities into one single group and form a dimensionless group. For example, in fluid mechanics, we know the Reynolds number. Abbreviated as RE. It is rho VL divided by mu. Rho is the density of the fluid, V is the velocity, L is the characteristic length of the problem. mu is the dynamic viscosity of the fluid. And you can check that the combination of these physical quantities give you a non-dimensional quantity. So all the dimension cancels. In non-dimensionless groups, they are extremely helpful because they often give you some hints or insights of the importance, relative importance of some process. For example, for Reynolds number, if you look at the numerator, you have a row. Row has a mass in it, and you have a feeling of something related to kinetics or momentum. And the v is velocity. Okay, now you have something related to velocity and something related to the mass. So you know that the numerator has something to do with inertia or the forces due to the kinetic movement. And in the denominator, it's the dynamic viscosity. So you know the ratio is the relative importance of the inertia versus viscosity of the fluid. And we will see many more dimensionless groups in this course. And each dimensionless number, as long as you just look at the physical meaning of the quantities in the numerator and the denominator, you will be able to tell what this number represent. Okay, now let's talk about operations on dimensions. Dimensions can be operated. The operation means you can multiply two dimensions together, or you can square a dimension, or you can divide the dimension together, make a division of dimensions. For example, when we talk about acceleration, A, we know that the dimension of A is length times squared. And when we write this, we are actually saying we using like division. We operate the division on dimensions. So that's what we mean. We can operate it in a similar way that we do algebraic symbols. So being able to operate on dimensions help us to recognize the relations between different terms and also the meaning of each quantities. Let's look at, before we look at a few examples, let's figure out how to write the dimensions of derivative and integration. So let's say if you have derivative, for example, dy dx, how to figure out the dimension of dy dx? If you know the dimension of y and x, the y can be displacement, the x can be time. And I'm just using generic symbols. So notice that derivative is nothing but the limit of quotations. So if you remember from calculus, dy dx means delta y divided by delta x, and you take the limit of delta x goes to 0. And if you see this division, you know how to deal with its dimension. So that means the dimension of dy dx is the same as the dimension of change of y and the change of x. And it's the same as the dimension of y divided by the dimension of x. So this is how you figure out the dimension of derivative. And then let's look at the integral. If you have y the function of x dx, and then you know also from calculus, it is when you take a limit to make delta x go to 0, and what you're doing is you do a summation. You sum over y evaluated at each xi delta x. So that means if you want to take the dimension of y ex, it's the same as you take the dimension of the summation of y xi delta x. And it's the same as the dimension of y multiplied by the dimension of x. Now as an exercise or as a homework, exercise, find the dimension of d squared y dx squared. A hint is you're going to use the definition of the second order derivative, which is you take the derivative of the first order derivative, and then you go from definition. You will be able to find the dimension of this. Okay, now let's look at a couple more examples that deals with physical quantities. So let's look at example 1. Find the dimension of shear stress. Oh. So in order to figure out the shear stress, we probably needed to first know how is the shear stress defined. And the shear stress is defined as the force applied on a surface per unit area of that surface. So it has the same dimension as pressure. In a sense, it's force per unit area. So the dimension of shear stress tau is the dimension of force divided by the dimension of area. Now, what's the dimension of the force? Force, you can think about what is force. If you think from the Newton's second law, F is ma, so it's mass multiplied by acceleration. So we know the dimension of force is mass multiplied by acceleration. Acceleration is length times square. Now divided by the dimension of A. The dimension of the area is length squared. So divided by length squared. And then you will get mass over length times squared. This is the dimension of shear stress. It's also the dimension of pressure. In SI unit, it is 1 Pascal. It's also the same as 1 kilogram per meter second squared. Continue this storyline. Let's look at some additional examples. So from fluid mechanics, we know that shear stress is related to fluid gradient by velocity gradient by this equation. This is for a Newtonian flow. A Newtonian fluid. So dV dx is the velocity gradient, and the mu is the dynamic viscosity. Now we just found what's the dimension of tau. And we also know velocity, so we know that tau, dimension of tau is mass per length times squared. And we also know that the dimension of velocity is length per unit of time, and the dimension of x, the x coordinate, is length. Now let's find the dimension of the dynamic viscosity mu. Well, you may already remember by heart what's the dynamic of, what's the unit or what's the dimension of the dynamic viscosity. Suppose you don't know, or suppose you don't remember by heart, but you somehow you know the stress and the velocity gradient relation for Newtonian fluid. So how can you recover or figure out what's the dimension of dynamic viscosity from this equation? And the way we solve this is to recognize that in this equation, the dimension on the right-hand side must be equal to the dimension of the left-hand side. Otherwise, there's no way you can equate two quantities of two different dimensions. So we know that from the equation, you take the dimension of tau would be the same as you take the dimension from the right-hand side dv dx. So we just said that you can operate on dimension by using multiplication. So that means the dimension of dynamic viscosity multiplied by the dimension of dv dt, sorry, dv dx, should be the same as tau. And the dimension of dv dx, now it's a derivative. We just discussed that it's the ratio of the two quantities. So you have the dimension of velocity divided by the dimension of x. Now you can move the terms, move around it. You can figure out the dimension of dynamic viscosity is the dimension of tau multiplied the dimension of x divided by the dimension of velocity. And then you put these together, you will find that it is mass, the unit length, and the time. So in SI unit, this is kilogram per meter second. And you will see that it is the same as Pascal times second. So if you have dynamic viscosity expressed in the SI units, it means the number is the dimension is sorry, the SI in SI units is Pascal time. So for example, water at room temperature, the dynamic viscosity is 0.001 Pascal second. So this is a number. It's good to remember, but if you don't remember, that's also fine. You can always find it on the website. See, it's good to know the relative, like the scale, which scale we are talking about. It's 10 to the minus 3 on the order of 10 to the minus 3 Pascal second. Okay, now let's look at one more example, which shows exponent. So we have been talking about the operations on dimensions, that saying, okay, you can follow the standard operation like multiplication, dimension, and take exponentiation means you can square it, you can cube it, etc. However, what happens if you have a special function, not necessarily special function, but like non-polynomial functions like logarithm, exponentials, and trigonometric functions. So for those functions, we call those transcendental functions. So such as log, exponential, trigonometric functions, etc. And for those, those functions must have dimensionless argument. For example, if you are saying sine of ax, now the argument is ax. The combination of ax, if you take the dimension of ax, it must be 1. That means it must be dimensionless. Now let's use these to look at a third example. So we know that the Boltzmann distribution is a probability distribution. So the probability tells you that the distribution is proportional to exponential of this term minus energy divided by kBt. Kb is called the Boltzmann constant. Now let's find the dimension of the Boltzmann constant. Now we know that the argument of this exponential function must be dimensionless. That means if you take the dimension of e divided by the dimension of kb, and then multiply the dimension of t. Here, this t is not the time. This t means the temperature. So here, E is energy. T is absolute temperature in Kelvin. So now this ratio of dimension must be one dimensionless. So then it tells us that the dimension of KB must be the dimension of E, energy, divided by the dimension of temperature. So what's the dimension of E? Well, the dimension of E, energy, and let's work it out. What's the dimension of E? If you know it, you can directly write it out. If you remember that by heart, you can write it out. If you don't remember it, you can always work from something you know. For example, you know that the energy of a particle, like a kinetic energy, is 1/2 mv squared. So you know that the dimension of the energy must be mass multiplied by velocity squared. So you know it must be mass multiplied by velocity squared. The velocity is length per unit of time, and this squared. So this is the dimension of energy. So we can see here we have m L squared T squared. And then divided by the dimension of temperature, which is we use K as the dimension of temperature. And then you can just write it this way. Now we have figured it out. And in SI unit, it's joule per Kelvin. Well, it's not surprising to say it's joule per Kelvin because if you look at this equation, the dimension of the Boltzmann constant is the dimension of energy divided by the dimension of temperature. Then it is joule per Kelvin as being consistent with the physical interpretation of the Boltzmann constant is the energy change per unit change of temperature. So here we use the fact that on the argument of the exponential function must be dimensionless, and then we can figure out the dimension of Boltzmann constant if we don't know it ahead of time. But if you already know the dimension, then you don't need to go through this exercise. This is just to give you a tool that you can relate dimensions of physical quantities in one equation. And then all your analysis should be self-consistent, and you should get all the terms being of the same dimension in an equation, and also the argument of those transcendental functions must be on one. Okay. Now let's look at one exercise. Let's see. Algorithms. So this will be the exercise that you are going to complete on your own as your homework. So consider this Schrodinger equation in one dimension. The reason I'm using Schrodinger equation is because at this point, most of you have no exposure to quantum mechanics. And the reason for this is I don't want you to rely on your pre-knowledge of anything to work on this problem. So if you have already learned this, learned the quantum mechanics, then it's easy for you to figure out the solution. The goal is suppose there is a equation, like someone give you an equation and you have never seen it. How do you use dimensional analysis to make sense of it? So what I can tell you is, okay, the I is the imaginary number. So the I imaginary number means I is defined as square root of -1. The H bar is called the reduced Planck constant, but we don't know what it is. And if you have no exposure to any quantum mechanics, you also don't know what it is. And this psi is the wave function. So for this problem, the hint is you don't need to know the dimension of the wave function in order to solve the problem. And t is time, m is the mass of the particle, and x is the position. So this is the Schrodinger equation in one dimension. Now you are going to use what we learned today. That means operate on dimensions and use the rule that each term, so you have three terms, one term on the left-hand side of the equation and two terms on the right-hand side of the equation. The three terms must have the same dimension. And you need to find the dimension and SI unit of the reduced Planck constant H bar, and also find the dimension and SI unit of the potential V. Okay, so before we end this topic, Let me just give you a chart of some common dimensions and their units and also what SI units. So in this course, we will use the metric units, and most likely we will use the SI units. Sometimes we may use centimeter or micron instead of meter, but we will not use anything like inch or feet in our class. And let's see. For mass, yes, we will use gram, kilogram type of things, but we will not use pound. And for time, sometimes we may use second, sometimes we may use hour, minutes. It depends on the need of the biotransport phenomena we are looking at. So for example, if you're talking about some fluid filtration rate, you may not worry about the filtration rate per second, but rather per hour or per day or per minute. So depending on the context, so we may use different time. But for length and the mass, we will definitely use the metric system. All right, thank you. See you next time.